Introduce Yongjung from KAIST.
Thank you very much. I'm very glad to be here. And actually, my first time I met Yongjung was at Brown University, so we have some people from Brown. And at that time was 60th birthday conference for the Professor Konstantin Daformusis. So ever since we have good relation. Okay. Sometimes, so my case, if I submit my paper, I don't want to talk about anymore. So I always try to talk about what I'm working on right now. So this is that one, and this is a joint work I'm working with Wemini in Minnesota. And right now, this is my South career. I'm visiting Shanghai East China Normal University, and so I'm there. He's also there, so we are working together for this kind of interesting thing. Okay. And this conference is conference on the kinetics and related topics. Mine belongs to the related one, and I really learn kinetics. Okay. So this talk is about ecology. So everybody knows that what is the logistic model. So let's say P of T is the total population at time T, and epsilon is the natural growth rate. So natural growth rate means, okay, suppose there are enormous amount of the resources. We can grow as much as we want. Then, okay, that's a natural growth rate. It's a growth rate minus death rate. Now capital K is the carrying capacity of the environment. Okay, your US or your Korea or your Iceland are all different, right? That's K is the carrying capacity. These are initial population. Then the row system model is just given this way. And the first term is the growth. Second one is negative effect due to the competition. Initial value. Okay, so if we want to normalize it in this way, then we get this equation. And this equation is definitely an ordinary differential equation, very simple. And this one has two steady state, SS, steady state. And first one is equal to 0, and that one is unstable. And the other one is equal to 1. Okay, that's a globally asymptotically stable steady state. So that's very simple and clear. So I use this notation. And this morning we also talked about stability. And stability is always an important issue. Now in this case, a little bit different. This one is asymptotical stability. So as time goes on, we want to see how this one converges. And this one is globally asymptotically stable. That means whatever your initial value is, eventually you're approaching to that. So that's that kind of stable steady state. Okay, now this is the OD model, and I'm more interested in the heterogeneity, spatial heterogeneity. So in this model gives very good information, but in the ecology people, they want to consider heterogeneity in space. So resources is not constant. And there's the initial population, which is not constant. Then what can you do? And then there are two sources for the heterogeneity. One is initial value, and it's the environment. Previously, this is 1. Now, instead of 1, now we have M of x. More interesting case will be there's a M of x and t. But okay, for convenience, okay, let's forget about the time variance in the resources, and let's think about it. Then actually, even if there are x, this is an ordinary differential equation for each x, right? So you can easily see that the solution converges to this one. If initial value at point x is 0, always x 0, positive, then growth of the M of x. So you can think M of x is just a local carrying capacity at that area. Okay. So this means, okay, there is no migration effect. And definitely migration is very important. You can move some other places, and then you can also grow there. So migration effect is kind of a strength. It's advantage. It should be advantage, not disadvantage. It should be advantage. So there are two kinds of migration effects. First one is diffusion. Second one is advection. Advection means you are going toward the food or this way. Migration and diffusion just move around. They are different. And in this talk, I'm just consider diffusion only. Then if we put the diffusion, then okay, just put this thing. D, okay, can be a constant. If D is not constant, if this somehow you have to rewrite this with the divergence and the gradient and put inside, right? So that D is a constant, and then okay, this is a linear diffusion. As a linear diffusion, you know the linear diffusion just models a random walk. So you have move just randomly. Okay? So that kind of thing I call mobility without purpose. You just move randomly, and it happens to you have got some food, you get some food and then move randomly. So this is the mobility without purpose. Okay, so this is diffusion, this is a reaction initial value. Now boundary condition, non-boundary condition, that means that the area is insulated. Nobody goes out, nobody comes in. So that's a boundary condition. And then if this M is just constant, 1, then equal 1 is still the globally asymptotically stable steady state. That's it. And these are all you know long time ago. And if M is not constant, then there exists some function which is non-constant and which is a unique global asymptotic stable state. So that's well known. And this theta D, so D, actually this theta depends on D and M. So this theta D is a perturbation of M of this resource function. And if D goes to 0, this converges to M. And if D goes to infinity, so diffusion becomes bigger and bigger, then you may expect that this one goes to the constant state, and this is the average of the resource. So these things very well. Okay, now I want to see the competition. Suppose there are two species. One is U, one is V. Diffusion, okay, everything same. Okay. Now in this model is called the competition model. The reason is U and V, they eat the same thing. So here is U plus V is in some sense total population. They eat the same thing, so minus. Okay? Probably if there are two different species, their weight can be different. Okay, just suppose they have same weight, so constant 1, 1, 1, 1. So the only difference between these two is the diffusion. So let's say D2 is bigger than D1. Okay? And then D2 is bigger, then diffusion of V is bigger, so I want to call V faster diffuser. Okay, and U is slower diffuser. The initial value is positive, same non-boundary condition. Then you will say, okay, they compete the same food. Then which one will win in this competition? That's very natural question. They can both survive, or one of them can extinct. Answer is one of them is extinct in this case. So it's about 1 year and 5 months ago when you asked me this question. My answer, probably. I always believe that diffusion, mobility should be an advantage. So best one will win. Answer, I was wrong. My answer was wrong. Slower wins. So that's in 1998. These people, the theory. And this system has two critical points. One is this. So theta D1 is the steady state of the single equation case, previous one, corresponding to D1. This is D2. And this one is global asymptotic stable state. The other one is unstable. And if this one is global asymptotic GASSS, that means this one already converges to this one, no matter what the initial value is. And that means this one wins, and the other extinct. So that's the story. It seems a little bit, I don't like this story. I always think, okay, mobility should be advantage, but here disadvantage. You can see that there's some reason. For example, let's M is this kind of, M is this one. Okay? Then U and V somehow try to, if there are more resources, population increase. So try to match this one. Okay? And if you have bigger diffusion, then the guy live here trying to move up. Right? That means somehow if you move, diffusion is high, those species has some tendency that give up the good place. So eventually that's the reason. Eventually they extinct. Okay. So if M is not constant, if M is constant, they both survive. But M is not constant in Yongjung, then okay, slow one prevail. Okay. So I tried with the experiment, numerical computation. So what I did is also use this. Suppose there's a new land, and there are two species. They arrive at the same place, and then now they start to grow. What will happen? Okay. And so this is numerical simulation. So x-axis is time. So this 50 is 50 time when t equals 50. This axis is for the total population. Okay? This is blue, this is slower diffuser. Red, faster diffuser, their total population. Initially, they are very small. But they are moving and they are growing. So you can easily see that the faster diffuser take advantage and they grow faster. And it looks like this is a steady state. Okay? So in this case, probably thinking, oh, the theory is wrong. Faster one is advantage. Okay? I think that is just because of the situation. They just arrive, nobody there. Okay, they are moving. In this stage, the faster diffuser better. Okay? The second stage, you wait a lot longer time. Now not equal 1,500. So it's a completely different time scale. Then eventually, faster diffuser decays and the slow diffuser wins. Okay? So really, this is always, if you do math, I think it's good to learn some kind of lesson, particularly young graduate students. Right? So being busy is no better than just being lazy. Okay, just work whatever without purpose. Okay. So this one just says being busy is no better than just being lazy. Okay, this one. But my title is this, without purpose. That is, if you have a purpose, search will be deeper. The data I have to tell you. Okay. So spatially heterogeneous diffusivity. Okay, now I have a different setting. Let's alpha will be my diffusivity. Okay, now diffusivity is not constant anymore. Diffusivity, so L is a low number, it's a lower diffusivity. H is a higher diffusivity, so H is bigger than L. Yeah, still. Now there are two species. Okay? Now there are still more resources. Then food is enough. Then okay, I think okay, food is enough. Then it's a lot better to stick to the food. So lower diffusion, M. Now here, M is less than the population. Then okay, better to looking for food and increase your diffusivity. Okay, that's a high. Okay, this is my alpha. So in this case, okay, so diffusivity has a purpose, finding a food. Now to this one here, this equation. Now U is still in the diffusion, but I put L, so it's a lower one, L. Okay. Now V, put alpha. Now this alpha is not constant anymore. It depends on X and T with M or all these things. So this one should now place inside here if it's not a constant, right? If it's a constant, you can take out, but it's an L constant, fine, but alpha is not. Okay, now let them compete. Which one will win? Which one will prevail? Do you guess? So no food, okay, higher diffusion. A lot of food, okay, lower diffusion. So I told my students that, okay, this case, this one, V, will win. And then, what surprising thing is, no, I was wrong. Still, the theory says, so we can show that. Very easy. The same proof, almost the same proof. Theta error, this one is asymptotic, global asymptotic stable state. Yeah. So I was surprised. So I talk with my students with confidence, but I was wrong. Sometimes that's right. So I also did the simulation. Now they are at the same place. There is no advantage. So there are enough food altogether. So both of them basically have the same diffusion. So they grow in the same way, right? But if you wait a little bit, now it split it, and the red one is below, blue one is above, and now this will show exactly the same long-term asymptotics. So slower diffuser still win. Okay. So in this example, H is 0.002, it's 0.001, 2 times difference. So I just did a different way. Okay, I make H smaller. So that means this guy is very stupid, right? You have a lot of food moves fast. No food moves slow. Okay, I think that's a very dumb thing to do. Okay? And then in that case, okay, so since L is bigger, U is now not faster diffuser with a linear diffusion. Now V, non-linear diffuser. But very dumb. I found that's so very dumb, but V wins. Okay, what's wrong? This is the thing. So I start to think that what we have about the diffusion equation is what we thought. And that's not what. So my conclusion is, okay, we are always using Higgs law for the diffusion, even for the biological settings. And I start to think that if we are talking about the biology, probably Higgs law is not good enough. Example. Okay, so what's Higgs law? Higgs law says that D is diffusivity. The flux is given in this way. That's simple. Higgs law. Now this is our equation. Now let's this epsilon is very, very small. Okay, even 0. That means both rate, death rate, same. What they are like never die without breathing. That's the case. Okay. So let's just for the simplest case. Okay, it's an interval. Initial value 0, 5. M is this. Then since interval is 2, total population is 1, M integration of M is now 1. So there are food, enough food that support this population. Okay? And suppose epsilon equals 0, then no matter what the diffusivity D is, you can choose various different way. D can be dependent on U or X, T, whatever. Whatever your D is. Solution is just that's obvious. It's not changing. So that means the diffusion we are using isn't a little bit it's very wrong for this kind of setting. Right? If you're live form, you're supposed to move the food, but this doesn't have that. I think this because of this one, many of the results, there are many paradoxical results in ecology. I think. And what we saw, the slower diffusion prevalent is also, I feel, related to this kind of problem. Okay? So what I thought is, okay, then let's review what the diffusion is. Okay? Okay, this is just 10 minutes left. So, let's see. So you know that diffusion comes, you can make a diffusion equation from the random mode. You know what's a random mode? For example, you divide into slices of delta x and then to the random mode. But that's not good enough to consider this case. And I'm presenting a different approach. So I want to derive diffusion equation from Brownian motion. So this is a little bit kind. So what's Brownian motion? Okay, you can guess there's particles. They are moving. If there's a particle, they always want to move straight. But there are too many of them, they collide. So they are the collision. So they are moving Brownian. They have Brownian motion. And what's diffusion? I understand diffusion in this way. Brownian motion is a very micro scale behavior. But what we are going to see is a macroscopic view. So diffusion is macroscopic view of micro scale behavior. Okay, so let's think. Delta t, delta. So delta 1, delta t is the time interval between two collisions. Beta 2, delta x is the length between two collisions. Now we delta t, delta x, that's a microscale constant. We think each system, okay, we just let that fixed. Now beta 1, beta 2, they may depend on x and t. And this beta, so we can say beta 1 or beta 2 equal 1, that means, okay, normal state. If they increase or they decrease, then okay, there's variation. And so beta 1, beta 2 is a macroscale quantity, but they are function of x and t, so they may vary in microscale way. Okay? Then, but the point is, we will see that the biological setting, this can vary in a macroscale way. Then that will give some different result. Okay, so anyway, the next k is a time period macroscale. Now let's say n is a k divided by this time scale. Then okay, since this is micro, this is macro, n we may assume n is large enough. Now their movement is the random movement. If random movement, if you make big number of random movements, their distribution at the final time t and k should follow normal distribution. So that's what you learn from the secondary probability class, right? Then suppose that you start from point y. Then the normal distribution is still the average is the same y. But the variance is just expectation over x squared. And then this is number of collisions, x squared, so x is better to delta x. The square of this, multiply this, then you get this. But since if beta 1, beta 2 is constant, then this alpha is exactly this. Okay, you can easily see that. But if they are not constant, alpha is in some sense average of this thing. And I want to call this alpha mobility. That's very reasonable. For example, if beta is small, then also okay, here's a collision distance and move from here to here with a small distance, small time, then means you have more mobility. And if beta 2 increase, what then means distance is longer. So it is also more mobility. So if this is ratio, we can call that mobility. That's increase, that's more fast. Okay. So, one more thing. So you can clearly see that if this one is constant, then even this one, even they are different kind of Brownian motion. If this ratio is same, then the macroscopic view identical, right? So that's it we call D. And people say that in a random walk, what they explain is this ratio should be fixed. Then you can get diffusion. Otherwise, you never get diffusion. That's the way they explain. But I think that's not the very correct explanation. The correct explanation is if this one is fixed, then those random motions, Brownian motions, show same diffusion. So macroscopic view is same if they are same. And then the normal distribution is just this. Okay. Now what we have to do is this is USD. Now I want to fix X. And I want to consider the flux. Okay, flux by the random walk, this kind of Brownian motion. So to compute the flux, what I have to compute is, okay, point fixed, point Y. So suppose there is a particle starting at that position, and I want to compute the probability that the particle starts from Y cross this line. Okay, that's what we have to do, right? That's the flux. Then this is the one, right? Very simple. This distance, and then integrate this one. For this. Is that correct? Is that sure? Okay. So the normal distribution is something like this. Now this is the starting point, Y. Now here is X. Then the probability that the particle starting from this one cross this point is this. That's the about the probability. So that's one. And do the computation, okay, this one is given by an error function. I think this is my first time to use error function. And the other one, so you start from this point, then the probability to cross this line, that is this. So what is a flux? Flux is a net amount of crossing this one. So this one is from the left hand side to right hand side, this is from right hand side to left hand side, then this is a flux. And this flux is very exact. Okay, now the flux is okay, instant. So we take k equals to 0. Okay, if k goes to 0, this one, the support is shrinking. Alright? And I want to estimate this one using single point. Okay? Then you get differential. My goal, okay, get a differential equation. Sometimes, if you want that, please I don't use that. But okay, then how? So you can see that this is the average of function u, and with this weight function. That's m. M is total mass. Okay, then this is m. I didn't compute by hand. I compute this one with the maple. Okay. Okay. And then central mass. Okay, this is central mass. And what you have to see is in both cases, see here is alpha k d. So if d is constant, k is constant, alpha is not constant. You may assume alpha is constant, then you return to the same diffusion. But my modality is not constant. But since still I choose one point approximation. Okay. And here, what is it? So m is the same. Alpha is not constant, but kd they are constant. So here is u is function of y. Alpha is also function of y, but we are going to just pick one point. How? Somehow. So I choose center of mass, C plus, C minus. Okay, so this is total sign of mass. So this is approximation of previous integration. Now we write them. Okay, now take the limit, then this converges to this. Okay, so what this one says. So probably after I got this one, what I have to check first is compare with the random walk thing. And the random walk case, beta 1, beta 2, they are just 1. Okay? So alpha equal 1. And then d is delta x squared over delta t. And this is exactly the same as the random walk. Okay, so they say. But this case, okay, alpha is not constant. The point is alpha is inside and outside. Previously, what I thought about is alpha outside only, not inside. So the equation is now this. And we can remove this to avoid 12K with the different, using different time scale. Summary. We know Furier's law about heat conduction. Furier's law, the flux is given in this way, and K is the heat conductivity, and theta is temperature. That's the flux of the heat transport. And Darcy's law, okay, P is now pressure, porosity, viscosity. Okay, that's the Darcy's law. Ohm's law, okay, this thing. Fick's law, U is concentration. So ours, okay, this is D. So this works if alpha is constant. Alpha is not constant, okay, this doesn't work. So our conclusion is this: if we consider
is the K is constant?
Which one?
Furier's law, K is constant.
No, don't need to be.
Don't need to.
Don't need to be constant. Okay, but this one is outside, not inside. Pressure, and then so I got some motivation from the Darcy's law. With the Darcy's law, for example, the gas law, then pressure depends on that gas density. So if you use the gamma law, like this P is density rho to this gamma. Gamma is bigger than 1 on this thing. But then another view seeing the pressure, gas density times temperature. Okay, our mobility is very like temperature. If the temperature increases, the mobility increases. Okay, so but here that difference. Here K is porosity, mu is viscosity. Now here. So this is our mobility, our flux. Then here D is this kind of diffusion ratio. Alpha is this mobility. Okay, U is the concentration. Point is so previously I had alpha outside only, but important thing is you have alpha inside. So this is my equation. Okay. And so now mobility with the proposed. Last time I told that diffusivity is the proposal. That's not enough. Mobility. So I got the same alpha. Okay, so one species case, okay. Now biological diffusion, diffusivity is alpha. Biological pressure, alpha U. Now, okay, summary. Okay, now I want to consider this case. If the biological case, this kind of mobility can be very natural. But more the gas element setting, this is not so interesting. But the biological setting, okay. I think this is a very crucial part. So our system is this. So one equation case. Okay, this one. Alpha M, okay, so let's just go to simplest case. Then basically in this kind of approach, the domain dependence is not so strong and dependency on N is not so strong, so you can easily extend to the general case. I want to show you just the simplest case. Now, M is, let's say, like a discontinuous circle. And B is bigger, alpha, A is smaller. Mobility, okay, this one. Then this problem has a unique globally asymptotic stable steady state. Okay, let's say this one, theta, alpha, M. And this one is exactly same as M if this ratio is bigger than this. So mobility difference is, if mobility difference is bigger than this one is resource difference. Okay? Then this one is exactly the same as M. Okay? And if M is more general case, this ratio should be replaced in that way. Then interesting. That's very utterly shocking for this kind of problems. M itself is the one. It's the globally speaking stable steady state. Okay. Then competition. Now we want to compete them. So let's U. This is just a linear division. Let's just D. V. Okay, this is my division. This very looks good. Okay. And then alpha same now. So the same way. And then okay, lower boundary condition. Okay, initial value is non-negative. Then if this mobility ratio is bigger than this resource ratio, then this one is globally asymptotic stable state. For all D. Whatever the D is, the small one wins. And if this ratio is natural, like this, then there exists D naught. Then this one is a global asymptotic state for all D bigger than D naught. And this D naught is less than L. Now furthermore, okay, if D is less than D naught, then two possibilities, two species may coexist, or this one can still prevail. So if this ratio is very small, okay, slower one still can still prevail. So conclusion is being busy with a purpose is a lot better than anyone without it. That's also you should work with some purpose. Thank you.